Hello, welcome back. In this video session you will see one more problem on the Holtzer method. It is for the free system. In the first problem we have solved this Holtzer method for the free and fixed system. Here you can see the first problem. Here it is a mass spring system where one end it is fixed and other end it is free. Okay, now we solve a problem where both ends are free. This type of systems are called as the semi-definitive systems, and it is a free system. For free system, both ends are, it is not fixed here. For both fixed ends, free systems, and one end is fixed and other end, for all the systems, the tabular column for the Holtzer's method, it is same. We are using the same 9 columns here. First one is position, second one it is assumed frequency, third column it is mass, fourth column it is displacement, fifth it is inertia force, sixth it is the summation of inertia force, seventh it is spring stiffness, eighth it is spring deflection, summation of inertia force divided by spring stiffness, and it is new displacement or the displacement of the next mass. Okay, what is the difference here? In the previous problem, one end it is fixed and the other end it is free. Now it is a free system. Free system, in the free system, the position you have to take it from the left side mass. It is position 1, it is position 2 and position 3. In case of one end it is fixed and the other end it is free, we are taking the position from the fixed end. Okay, now we are taking the position for the free system from the left end mass. It is position 1, position 2, position 3. So you are taking position 1, 2, 3 in the tabular column. Position 1, 2, 3, and then you assume a frequency. You can use the rough approximation by using this equation: omega is equal to square root of k by m, where k is the equivalent spring stiffness. We have two spring stiffness, so you use this equation to find the equivalent spring stiffness value. Then you take assumed frequency by using this. Now for this calculated value, it is 1.29. you can take 0.1 or 0.25 or 0.2, any value, okay, as the assumed frequency. In this problem the author have taken 0.5 as the assumed frequency. Next, masses. What is the mass at position 1, position 2, position 3? It is 2, 4, 2. We will see in the figure. Okay, m1 it is 2 kg, m2 it is 4 kg, m3 it is 2 kg. So 2, 4, 2 masses. For in the position 1 it is 2, 4 and 2. Now we already know that we need to assume the initial displacement for the first mass or the mass which is at the position 1. It is always 1. For the convenience purpose, you are assuming the first mass as the displacement of the mass at the position 1. It is 1. Okay, then you find the inertia force using this equation. M, what is the m here? It is mass into displacement into omega value, omega square, it is 0.25. okay, product of this mass, displacement and omega square, it gives you inertia force. Next is summation of inertia force. As of now we have only know this inertia force, so you keep the same value. Next, spring stiffness. You mention the spring stiffness value from the left end only. We have only two spring stiffness, so this is the first spring stiffness. K1 it is 5 Newton per meter, K2 it is 10. So 5 and 10 are these two spring stiffness value. You mention it from the left end. Now summation of this inertia force divided by spring stiffness. Summation of inertia force, it is 0.5 divided by spring stiffness value. Spring stiffness it is 5, so it is 0.1. okay, the spring deflection of the second mass, it is fourth column, it is displacement, it is 1 minus this 0.1, it is 0.9. okay, this displacement can be calculated by fourth column minus eighth column. okay, see here what is the this all calculation, it is same as for all the systems, whether it is free system, free fixed system or fixed system. But the only difference here, when you take this all the values in the graph, in the x-axis it is frequency, and in the y-axis now you are considering the inertia force, okay, not the displacement. For the free systems you are considering the inertia force, sum of inertia force, that is you are taking the value in the 6th column. Okay, for this frequency, for 0.5 frequency, what is the inertia force, sum of inertia force? It is 1.78. okay, similarly for 0.75 inertia force is 3.48. okay, for 0.5 this much is the inertia force, for 1 this much is the inertia force. Okay, then connecting all the points we have this curve. Okay, wherever you see natural frequency 0, that is the natural frequency of the system. For semi-definitive system or free systems, always you take the first natural frequency as 0. okay, then by using this tabular column you find other two values. You are only looking for two change in the signs. Okay, for the first assumed frequency it is positive value, so now you look for you are expecting negative inertia force. For this value also it is positive. For this value it is positive. For 1.25 it is positive value. So for omega 1.75 this is a negative value. One time there is change in the sign. Now you expect one more time, minus to minus, minus to minus, minus to minus, minus to minus, minus to plus. Okay, now there is 2 time change in the sign. So the first natural frequency for the semi-definitive systems or the free system, it is 0. Now you take all these natural frequency in the x-axis and all these inertia forces, what it is highlighted here in the rectangular box, it is in the y-axis. When you add all the points you will get this curve. Okay, you just find wherever you will get omega value is 0. So first natural frequency it is 0, second natural frequency where the curve crossing this x-axis it is 1.75, and again this curve cutting this x-axis it is 2.85. so these are the 3 natural frequency for this system. Okay, what is the difference here? Now you are for the free systems you are taking the y-axis values are the inertia forces, and this position value you are taking from the left hand. These are the 2 main changes in the for the free systems comparing to the one end fixed and the other end free. Okay, similarly for what is the difference between mass spring system and torsional systems? In the mass spring systems it is just similar to torsional system. Both systems are same. Instead of mass we are considering here I value. Okay, to find the instead of masses we are considering moment of inertia. Instead of displacement we are considering angular displacements. Instead of inertia forces, instead of mass you take inertia, instead of x value you take theta value. Okay, that is the difference for the spring systems and the torsional systems. Okay, thank you very much.